in one section.
Yeah, I was looking at the last constructions.
Like I told you, the constructions do get very ugly towards the end.
Well, why does everything in math have to get ugly? I did simple days in first grade where it's 1 plus 1, and that's where we left it.
You know, I don't have many memories of first grade, but that is one of my memories, was literally looking at the number line, and our number line in our classroom only went to 10, and I kept thinking to myself, well, there must be numbers past 10. And like, you know, this was first grade, and we didn't do math in first grade past 10. No, it wasn't today, but.
What? You're telling me there's an 11?
Well, no. I kind of put it together. I mean, like, I kind of figured it out. I should have known I was going to be a math teacher at that point, but I thought about it myself. I was like, well, there must be numbers past 10. And then I would say, well, there's two numbers past 10. What would that be? And, you know.
11 and 12.
And that's why, it goes back to the fact that, you know, math is not a construct of humans. It's just math exists type thing.
Oh, dear.
And there's 4 of them today.
4 of them, that's not too bad, unless they're like big theorem.
All right, who's on? Ben? Ben's on. All right.
Oh, dang, I have to do proofs again. I thought we were done with proofs. We really just said that we had to do proofs. Well,
all right, the computer will not die today because we're not doing any construction, so I'm not having it face.
Good.
All right. These are, the proofs are, well, once you see the first one, the rest are kind of similar to it. And these are challenging proofs in the sense that you have to think about it for a while. If there's a class with the most craziest verbiage and the craziest ideas, it's this one right here. Even today, every time I teach this, I got to keep it straight in my head. Like, I don't, even today, I'm a math teacher, I don't have these words memorized. It might be because I don't do it enough and I probably should have it memorized. I'm just saying that these words never stuck with me. I know the concept really well. We get one formula today as well too, but there's going to be 5 vocabulary words, 4 concepts and 5 vocabulary words, and boy, do I find it hard to remember these things. Well, luckily you have a book of truth. Questions on the homework?
It was homework. I did
Yeah.
a lot of drawing.
Let's take a look at number 5. That period was number 7.
Oh, no.
Yours is number 5.
No, we just have to do what we did for construction 7, I think.
It's the same thing. It's just an angle.
Yeah.
McKinley on top of it. Yes, he is correct. So we need to make the parallel through this angle through F. So we need to make it parallel. So you have an angle.
Really?
You got an angle EDF. So we got EDF, and we want to make it parallel. Where's my ego? We want to make it parallel to ED, but it go through F. So I guess, I don't know, in the big picture, just ignore this line right here, right? And just do that process that we did yesterday. So let's see, what was the first process? What was the first thing we did?
Draw a line from point A to a given point.
Okay, so where is that on this one? We need to make it parallel to this. So, I mean, we can imagine what's going to happen, right? It's going to look like this. So what do we need to do? We need to make a line. If you think about it and you turn this whole thing so it looks like we did yesterday, so the line that we're going to construct is going to go through DF. And that's the angle that we're going to replicate right there. Okay. So it's just turn, and you have this extra thing as well too. If you want to, in your mind's eye, erase that and then do that. Okay, so then we open up the compass, we make that arc, and then we go here from this point right here, we make that arc, and we measure this arc, right? And then we place that on this piece right here, and it gets to be about, I don't know, like right there. And then clearly, it's not good when I freehand it, but that's the basic idea.
I hate Jerusalem.
What?
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 What? All I did, I don't even remember that. I just make corresponding angles.
So
I don't even remember the procedure.
let's draw it. I need to make it go through here that's parallel to that. So Another way you could do it is you could measure this angle, and you could create, because what you're describing that, I wouldn't do corresponding, I might do alternate interior.
I just did the one.
So for instance, we know that that's what we're trying to make. So we know that these two would be alternate interior. So what I could do is measure this one. In other words, make the arc right here, then come over here and put it like that.
Yeah.
And then measure that and go from right here and go like that. That would be another way. I like that way a little bit better than the previous way. Okay. Corresponding, then you would be making that angle right there. Okay. So arc, measure, measure.
Are we doing the what's it called? The it's called the circumcenter and the inscribed center or whatever.
Yes, that is what we're doing. There's 4 of these. All right. And they're just not memorable. They're words, and you'll recognize them, but you'll forget which one applies to which. Okay. So I'll collect the homework. There's actually no actual answers. Answers other than the construction. I'll just give you the forewarning, and I did it for my other class too. Questions 9 and 10 will be on the test. So question 9 says, how do you make a 45-degree angle? How do you construct one, McKinley? How do you construct a 45-degree angle?
Well, let's see. All you have to do is get out.
Without a protractor.
You kind of eyeball it.
I literally had all my kids from period 2 say, well, I just pulled my protractor and I made it. I'm like, no, we don't have a protractor. All we have is a compass and a straight edge.
Oh, I know how to do it.
Now, let McKinley stew on this for a little bit.
What?
How do we make a 45-degree angle?
You mean exact or?
Exact, with a compass and a straight edge.
A compass. All right. So you make first you use the straight edge to make a straight line. Okay. Then you turn the straight edge up and make a line straight up.
How do you make it straight up?
Oh, you put it on the end of that's a line, and then you put go up. Not that way, straight up.
Well, how do I know what's straight up?
But that's straight up if you're in China.
Well,
how do I make it go straight up?
You go up north.
How do I make it go up north?
By drawing it up north.
But how do I know it's up north?
How do you know it's not an 89-degree angle?
How about construction number
7,
which says to make a
geez,
perpendicular line? Okay, so we can use, I don't know if that's construction 7 or not, but no, that's parallels. It's number 7. How about number 6? Okay, great. I made a perpendicular line. By the way, that's not 45, that's 90. Now what?
And all you have to do is slowly move down.
How about we use construction?
The
2.
7.
It's like 2.
Is it 2 or 3?
2. Or no, 3.
3. Construction 3, McKinley, is?
Construction number 3.
Which is?
Angle bisector drawing.
Why would we want to bisect this angle?
Because
why am I pointing there and asking you that question?
Because we're trying to make that the 3rd line thing that's in those.
Why would we want to bisect that angle?
Because you want to get 45 degrees.
Right, and if it's 90, half of 90 is 45. This is what period 2 did not realize. Okay, so this is 45. By the way, remember to make an angle bisector, the process is?
Like that, and then comes like that, and then you go from each.
You make an arc, and we open it up, or don't open up, leave it the same distance, and we go from here and here, and we make arc, arc. That's it. It's really quickly done. But you got to remember that, or you got to open up your book of truth. Okay, the other one they wanted you to make was 135. How are we going to make 135? What?
I did not
So
say.
you make the perpendicular line, and then you make another bisector, and then you just combine the 90.
You could do that. You could also just say, look what I just did.
We already have it.
Yeah.
Where is it?
It's right there, the other side.
The other side is 135. I love putting this question on it because the kids are paying attention or be like, well, I don't need to do another construction. I already made a 135 right there.
Well, what if you're not good at this at all?
That's why I asked you the question first. So hopefully that you would remember this so that when we get to test day that you do this and it doesn't cause too much problem. The other one was 22.5 degrees. Well, that's half of 45. How about 105? Where are we getting 105 from?
Can bisect the 45?
Bisect of 45 would be 22.5. I need to get to 105. How do we get to 105? By the way, this is question number 12. You were supposed to do it last night.
I did do it last night.
So how did you make 105 degrees without a protractor?
Took my protractor and I put a little dot at
I know you did, which is all the period 2 did as well too. It doesn't say use your protractor, it says construct. So how do we make 105 degrees?
You make a 105 degree arch.
How do we get to 100? Well, we can't subtract these two. That didn't work. How do we get to 105?
You have to subtract 30 from 135 or add.
Yeah,
15.
but 30 is hard to get with a compass.
How do you get 15 with the compass?
How are we going to get to 105? Well, we've seen how we get to 45. We've seen how we get to 90. We've seen how we get to 135.
What's 11.25? No, right.
How do we get to 105? Nothing? Well, stew on that. I'll tell you at the end of class.
Well, if you can't solve
I
it,
will
Jack,
think about it.
I will give you an 1 point X credit. By the end of class, you can figure out how we get to 105.
Cool. I want to do my.
Jack, if you don't solve it, you go on a crusade with me.
All right.
Well,
I will probably, I don't know. No, I still got to do a mini review because they got to do the construction. Yeah, we will follow this. We're going to be a day off for a while.
what if Thursday is?
No, you guys are just be a day ahead of them. It's no big deal. All right, here's your homework.
It's gonna be so stupid. I'm gonna hit myself in the face.
Why don't you just use the protractor and pretend like you did it all by yourself?
That's what I did on my homework.
Well, there wouldn't be marks on it then, so you'd be able to tell.
Maybe not if you erase all the marks and make it really delicate. And then boom.
Just add some
And this is an A question.
This isn't, well, it's the last, or second to last A question.
And 13 wasn't even that hard.
Agreed. Cut things in
13
half.
was really easy. I just used a ruler.
No! You can't do that. To make 3/4, you cut something in half, and you cut it in half again.
Yeah, I know. I was joking. It was
Okay.
a joke, man.
Good joke, good joke.
He's not joking. Yes, we did it. I'm pretty sure.
Period 2 did. They told me they did.
Oh yeah. Well, guess what? I'm gonna when my picture of my homework, you're gonna see I totally did do it.
I believe
Well,
you
if
did.
it's a sure he's not going to show me the pictures for now. I think my theory is right.
That dinosaurs didn't eat grass.
Yes, I still believe that, and I will research that. And if I fail, then I will eat chocolate.
All right, here we go. Getting going here. I need everything in your book of truth. Everything in your book of truth today.
Everything.
All right, because you're not going to remember this stuff. All right, here we go. We're going to take a break from constructions. Today, the words are very confusing, and even some of the ideas are confusing in the sense of, boy, they deal with the same 4 things, seemingly, 1 triangle, and 4 things about a triangle, and you get all these words. All right, there will be 1 formula we get. So 4 concept, it says 4 main, but I'm going to give you 5 vocabulary words, but 4 of them are the main words. Right? 1 of them is easy to forget about. All right, I've never had anyone that can keep this straight in their heads, right? Like they literally, I'll teach it to them, and then, 4 days later, I'll ask them, and they're like, oh, it's this one. They're like, oh, wait, is that the one where we deal with this or that or that? You don't forget the basic idea, but you forget the names. So when the book says make this, and you don't know what the name is, then you're screwed. All right, write this down, book truth. Concurrent lines. These are when lines, 2 or more, intersect at 1 point.
Okay.
2 or more lines intersect at 1 point, like that.
Most lines.
What?
Most lines.
Most lines? What do you mean?
Most lines are concurrent.
No, most lines are not concurrent.
If you have 2 of them, most likely concurrent.
2 of them, I'll agree with you. But when you deal with more than two, most times lines are not concurrent.
Right. Except for.
Okay. Here are three lines that are concurrent. McKinley, why are these three lines concurrent?
Because they all intersect at one point.
What about these three lines?
They
all intersect.
They do not, they're not. Because they don't intersect at one point.
And that's the idea of concurrent lines. All right. That's the easy word, and you won't forget that one. You won't forget the rest of this stuff. So now we're going to deal with these 4 words, 4 proofs, 4 theorems, 1 formula. The very last one we do is the one we get the formula from. The rest of them, there's no formulas. There's just the idea that they make concurrent lines. All right, here we go. By the way, I don't know if you remember, this is many chapters ago. I said, hey, it was a triangle and they had to do something with a triangle. And I said, we will talk about this way long, right before spring break. Now we're going to talk about it. All right, so here's the proof. So just watch me do the proof. You don't need to write down. So I'm going to get a triangle. Nothing special about the triangle. Could be any kind of triangle. And I'm going to make angle bisectors of the 3 vertices. I'm going to prove to you that the angle bisectors all come together at one point, so a point of concurrency. And then further, that point, wherever that point winds up being, maybe it's right here, that point is equidistant to the 3 sides. Now, clearly my point isn't right there, so that can't be the point. That must be a little bit lower, so maybe right here. But this point right there ends up being equidistant to the sides. You're like, well, that isn't too complicated to wrap your head around. You agree. But when we add the other 3, it all just jumbles together in your brain. Okay, so I got to prove 2 things in one proof. I got to prove that these 3 angle bisectors all form a 1 single point, they're concurrent. And then 2, that point is equidistant to the 3 sides. Seemingly a very the proof is actually pretty easy, just no one ever remembers this. Okay. So here's what I'm going to do. Would you agree that if I extended 2 of the angle bisectors that they must intersect?
Yeah.
Okay, so I'm going to pick 2, and it doesn't matter which 2. I'll pick the bottom 2. So I'm going to pick the bottom 2. I'm going to intersect them at point. I believe that's an I or an L. I don't know which one.
Wait, now all you do is extend C and then boom.
Yeah, but we're not guaranteed that it intersects at that point, right? It looks like it should, but
it has to only. It can only intersect
well,
at that
we
point.
don't know that.
But it can only. There's no other way the others would intersect.
Why? Prove it.
Because lines go on straight forever. And
Yeah, but how do we know that would go right to there?
Because
only because I drew it that way, which I did, by the way.
Well, if I take a protractor and do that, it will go straight through there.
I'm not arguing that. I'm saying prove it, though. Don't prove it for one triangle. Prove it for all triangles. That's why we're doing this proof.
Well,
okay.
That's because lines always go straight.
So it doesn't matter that lines always go straight. You're not guaranteed that it intersects that unless you prove it, which is what we're about to do. All right, so here's the proof. We got to remember back. Oh, by the way, we did that by construction. So here's the idea next. I'm trying to prove that this point is equidistant to the 3 sides. So the first thing I'm going to do is I'm going to make perpendiculars, because remember, we measure distance perpendicularly. It doesn't come out very well in my presentation here, but you need to open up your book. From point L or I right here, I've extended perpendiculars. I'm going to prove that these 3 red marks right there, they're all equal to each other. And it looks like an impossible thing. By the way, I still haven't connected C to it yet. I haven't proved that part. Turns out that's really easy to prove. Watch me. We know that if you are on an angle bisector, from way back when, chapter 3, if you're on an angle bisector, anywhere on an angle bisector, what can you tell me about the distance to the sides? They're the same. So just by calling that one theorem right there, I've just now called it that's congruent to that. I've got this angle right here. That's an angle bisector, so that's congruent to that. So there are 3 of them are congruent to each other. Boom, done. That was crazy easy to prove. Okay, I forget the number of that one, right? But that's basically what it is. And by the way, I got to have one extra statement because of transitive. If IT is equal to IR and IR is equal to IS, then IT is equal to IS. Okay. So there, half of the proof is done. I've just shown that that point right there, where 2 of the angle bisectors intersect, is equidistant to 3 sides. Now I just got to prove that C goes through this point. It's either I or L. I forget what I call I, it looks like. All right. Well, once again, point I is, from the previous statement, equidistant to the two sides. And we had a converse to that one. And it says that if you are equidistant to the two sides, you only live in one spot. You live on the angle by. If you are equidistant to the two sides, we just proved that, and you have to live on the angle bisector. Okay, that was actually pretty easy to prove. I mean, it's a lot, but it was pretty easy to prove. Okay, 10-1, write this down. Theorem 10-1 says this. We're talking about a triangle. If you have a triangle and you have three angle bisectors of the vertices, right? Black is the starting point. If you have angle bisectors, two things. One, those angle bisectors all meet at one point. And then two, in red, that point is equidistant to the three sides. So black is the setup. Red, in this case yellow, red is the so what. They intersect and it's equidistant to the three sides.
So wouldn't that be...
Further, we're going to give a name to that point. It's going to have a name and you're not going to remember it. But you will because it'll be in your book of truth.
How are you supposed to split an angle into three parts?
Sorry?
Are you supposed to split an angle into three different parts?
What are you talking about?
Congruent part. I'm talking about last night.
Oh, you're still trying to do 13 or 12? All right. You're not going to be happy when I tell you the answer.
No, I'm not.
Did you have this written down, by the way? Don't lie, though. Don't say yes.
I have everything. I have all through 10 and 4.
Okay. I saw you writing earlier. It'd be nice if that was called the Fred or something like that. It'd be memorable. It's not. That point right there, right? Write this down. It's called the incenter. Now we had inscribed angle. Now we have something called an incenter. Okay, well, that kind of makes sense. The point was inside the triangle. It would be great if the other three words were as equally descriptive. They're not. And they all sound like this. This is the one. The incenter is made by angle bisectors. And the so what about it is that the incenter is equidistant to the three sides. And they're all congruent. So if black, if you have angle bisectors, then red, hey, you're equidistant to the three sides. And you're called the incenter. Notice that their point of concurrency, they label it I. And then on the other examples, they choose letters that don't match this word. Right? I hate that. I need to change that for next year, but I copied it right from the book. It's not that it has to be called that, but the next one we do, it's not going to be this letter doesn't match that letter. All right, incenter. Questions? Oh, by the way, no formulas, but if you know that this is 3, then they're all 3. And that's the so what. But it has to be constructed with angle bisectors. McKinley, we good? Okay, next one. All right, 3 to go after this one. Or 2 to go after this one. Here we go. Not angle bisectors, but what is it? Not angle bisectors, but perpendicular bisectors. You see why this is going to be confusing? One's dealing with angle bisectors. Now we got perpendicular bisectors. All right, one word different, perpendicular. All right, so I'm going to prove not the same thing, not that the point is equidistant to the side. See why it's confusing? I'm going to prove that the point is equidistant to the vertices. In center, equidistant to the sides. This thing, I'll tell you the word here in a second, equidistant to the vertices. This is why it's very confusing. Not the concept, but like which one goes with which. Okay, hey, this proof is exactly the same as the previous one. Okay, I'm going to extend 2 of them, see where they intersect. They have to intersect. If they intersect, when they intersect, I should say, then I'm trying to prove that this point we're going to call O now is equidistant to the vertices. So I'm going to draw that. Okay, I'm going to draw the 3 red lines that would go from the point of concurrency to the vertices. Okay, cool. we had another theorem that said that if you are on a perpendicular bisector, what is the relation anywhere on this perpendicular bisector? What is your relationship to the two endpoints? It was a question on a test, and you all got it right.
I did.
What's the relationship between this point and the two endpoints?
To make a triangle.
Clearly,
Well, you asked what the relationship, and that's.
I mean mathematical, like number wise.
Okay, they all are 90. They,
What's the relationship between this side and this side? They're congruent. So guess what? Point O lives on a perpendicular bisector. That means it is equidistant to the two vertices, right? Two of the vertices. So just like the previous one, it's one statement, we're almost done. It's one statement, we're almost done. Because you're living on a perpendicular bisector, you are equidistant to the two endpoints. So it's going to be the same darn thing in a transitive statement. So just like that, I'm knowing half of it. Now I've got to prove that, well, this unnamed ray also intersects at that point of concurrency. We're going to do the same thing. You just proved that OA is congruent to OB. Therefore, it is the converse to this statement right here. Therefore, if you are equidistant to two endpoints, then you must live on a perpendicular bisector, okay, which is that one right there. There's only one perpendicular bisector of AB. There you go. That's lots of words, duh, right? We've shown it. 10-2. 10-2 sounds exactly like 10-1, except instead of angle bisectors, we have perpendicular bisectors. Instead of 10-1, 10-1 says then you're equidistant to the three sides, you're equidistant to the three vertices. Black is the setup, red is the result. No formulas, you're just equidistant to the three corners, the three vertices. And it will have a name, and I wish this was a C instead of an O, because we're going to use O later on. I don't know why the book put it as an O. It should be point C. It's because they set the triangle as ABC, they couldn't use C. So angle bisectors, you have something called an incenter. Perpendicular bisectors, if you read ahead, what's it called? It's called a circumcenter, which I'll give you a slide here in a second. I mean, the words just kind of just ramble around, and it's really hard to remember which is which.
I remember incenter.
Well, because it's the first one we do, but you also then got to remember that it's made with angle bisectors.
And because it's the center of the circle.
It's not necessarily the center of the triangle.
Well, I'm saying it's the center of the circle.
If you really wanted to talk about centers, I think this one might have a better argument that it's the center. By the way, it's not the center either, but it has a better argument because it's equidistant to the three vertices. We good?
Wait,
I'm going to show you what mathematicians would define as the center of the triangle here in a second.
I'm talking about the center of the circle, the inscribed circle.
Now what was your statement?
Saying that I remember incenter because it's the center.
Oh, got you. Okay. All right, so that concurrency we are going to call the circumcenter. Like I said, and if you don't have it in your book of truth and all of a sudden they throw that word at you, you're going to probably have to look it up. Wait, is that the one for angle bisector? Or is that the one for perpendicular bisector? Oh, it's the one for perpendicular bisectors. And further, that means it's equidistant to the three vertices. There's 4 of these. We've only done 2 and it's already confusing. We got 2 more left.
Well, we don't have theorems after this.
Yes, we do.
Oh, so I guess we're not proving chapter 13. All right.
The next one we won't prove.
Aha, I was right. Does that mean
The last one is the one that we're going to get a formula from.
Does that mean I get chocolate?
No.
No? Okay.
This is only 2 pages. Boy, why does this class take so long to teach? No, I lied. There's 4 theorems. All right, here we go. We good? All right. Yeah. Yeah, I agree. It's confusing. All right, 2 down, 2 to go. All right, this is not a proof. I'm not proving this one. Here we go. What's an altitude?
one side, but it goes. Oh, I see.
What's an altitude?
Angle to opposite side, middle.
Nope, that's a median.
And altitude is the line from the vertex that makes 90 degrees.
So it comes from an opposite vertex and it makes a 90-degree angle. So if I were to draw for this acute angle, the altitude, it would be straight down 90 degrees, right? Well, there's three sides, there's three altitudes, ready? All right, watch me. Well, there's an altitude. There's an altitude. And there's an altitude. If it's acute, the point of concurrency will be inside the triangle. Okay, if it's acute. Right triangles. Well, this one's already 90. So here are two altitudes right here. Where's the third altitude?
From the right angle
So where is the point of concurrency for right triangles?
up the vertex.
Well, that's what it appears to be, right? We're going to say it's on the triangle. Okay. What do you think about for obtuse?
It's off.
This one's hard to imagine, but watch. Well, this one's the easy altitude to draw, right? Suspiciously, I drew it that long. All right. We got to extend this other sides to make altitudes, right? So if I extend that side right there, because remember, we got to go to that vertex. So then there's the altitude for that one. It's pointing in the wrong direction, right? And then if I make the last one, let's see, what do I got? I got to go to this one right here. So I need to extend this and then draw that. It looks like these don't intersect.
If you look at that.
I go in the opposite direction. You notice now they do intersect. Okay. So there's nothing here other than a basic observation. Is that when we draw altitudes, once again, not a proof. I have not proven this, by the way. I'm suggesting that it's true. That for acute ones, the altitudes intersect inside, on, and outside. We're going to give this a name. We get nothing from it. Nothing. Notice it doesn't say anything about, hey, it's equidistance or anything. It's just a point of concurrency. This is probably the most memorable word that I give you, and we get nothing from it. Interestingly enough. Okay. So acute is inside, right is on, and obtuse is outside. If you forget this, you could just simply draw that type of triangle and prove it to yourself really quickly. All right, so this is 10.3. We're going to prove it in chapter 13. We can't prove it right now. That they actually have a point. We need some extra information. Okay.
Well,
We will prove it in chapter 13. You're going to have to trust me that we will prove it. And it just simply says that the altitudes of a triangle intersect at a point of concurrency. That's all it says. It doesn't say anything other than they intersect. If I were writing a geometry book, I mean, this is kind of neat, but it's not very useful in the sense of I didn't get a formula from it. And you didn't give me any sort of mathematical relationship other than the three altitudes intersect. And this is also why I believe that this is the shortest theorem in the entire book. I mean, it's only like, what, 6 words, 7 words? The altitudes of a triangle intersect at a point. And that's it. Kind of not very useful, right? It is interesting the fact that they do intersect. And we are talking about point concurrency. All right, I said 4. We got 3. Oh, by the way, the word for this one. Word for this one?
I don't remember this.
Neither do I, right? I mean, I do remember, but I'm just saying they are not memorable. Intersecting altitudes are called an orthocenter. I don't know why I find this word fascinating, but it's called an orthocenter.
What the heck is an orthocenter?
Latin people? Ortho? Where have you heard ortho from?
Orthos.
What? Orthodontist? What does that mean?
Like where you get your braces.
I know, but what in the world has that got to do with altitudes of a triangle?
Nothing.
They both hurt.
I was hoping one of you would know what ortho means.
I don't know. I've never seen that as a Latin word. Probably Greek.
Could be. I'm betting it's Latin, though. Orthography? You ever heard that before? Hey Siri, what is the definition of orthography? Oh, I'm sorry, I got on mute. Have you ever heard that before? Orthography? I actually learned this 3 years ago when I started working here. I never heard of it either. Hey Siri, what is the definition of orthography?
The conventional spelling system of a language.
It's how you spell words.
Do you want to hear them?
Crazy, right? We were learning about when schools first started in America, and one of the subjects they had was orthography. We were like, orthography? What the heck is that? Spelling. Orthography? Ortho center? Orthodontist?
Could it also mean taking your lease or lease?
No. All right. Last one. We will get a formula from this one. We'll spend a little bit of time on. This is the only one we get a formula from. The rest of them, you're either equidistant from the vertices or equidistant from the three sides. Okay. Medians. Remember medians? You don't need to write this down if you don't want to. Right? What was a median? I go from
the angle to
the vertex to the middle of the opposite side. So I'm going to go from the vertex to the middle of the opposite side. Okay, so let's see. The middle of the side, could we measure that? Could we split that in half using our compass? Could we cut the segments in half with our compass? Yeah. If I have time, I'd do that. I don't have time right now. So let's see. The middle will be here. The middle will be here. The middle will be here. No, that's not right. The middle will be here. If I draw from here to here, from here to here, and from here to there, we find that they intersect. Okay? We don't have enough time. I want to make sure we got 10 minutes left. I want to make sure we get to this. So they intersect at a point of concurrency. I did not prove that, by the way. I'm suggesting that they intersect. That point of concurrency will be called, last one, the only one we're going to get a formula from is called the centroid.
Like
it is called the centroid. It is the only one we get a formula from. By the way, this is also one that we have to prove later on in chapter 13, I believe.
Wait.
Centroid is the coolest one of them all. Centroid is also, if you ever have a triangle and you want to balance it on your finger, find the centroid. All triangles will balance at its centroid. Kind of interesting.
All right.
So if there was a middle, this is the middle. We're talking about mass of something. This is how you balance a triangle.
All right, where's the triangle at?
If you want to, we have to have a fixed one. So.
All right.
All right. We have it written down. We do get a formula from this. All right. It's the center of balance of a triangle. All right. Here's the math. This is Theorem 10.4. We're going to prove it in chapter 13. This is the weakest instruction that I will give because I should never in a geometry class say, look at the shape and tell me what you can tell from the picture without any marking. So look at the shape. Do you see that each one of the medians has a long piece and a short piece? Can you see that? So where is the long piece on CO? And where's the short piece? McKinley, where is the long piece on BN?
BX.
Where's the short piece? Okay, that's what you have to be able to do. This is weak, right? I shouldn't say you just look at it. That's not really geometry. Look at it and tell me. We're not supposed to tell anything unless it's actually got a physical marking. But yes, that's what you're going to have to do. You have to find the short piece and the long piece. Jack, did you already read ahead? Do you know the relationship?
I didn't read it. I just wrote it down.
Okay, so what's the relationship?
Using the triangle
For centroid.
that is 2/3 of the distance from each vertex to the midpoint of the opposite side.
Okay, write that down.
So AX equals
The short piece is 1/3, the long piece is 2/3. 1/3, 2/3, short piece, long piece. The whole thing, of course, is 3/3, but the mathematical relationship is 1/3, 2/3. You look at the short piece, it's 1/3 of the whole thing. You look at the long piece. Now we're not saying at all that unless it's equilateral, we're not saying that these medians are all the same size. They could be completely different sizes. But if you're looking at one specific median, then the short piece of it is 1/3, the long piece is 2/3. It's the only formula we get. Centroid. I started the class by saying it's 4 words. We got in-center, circumcenter, orthocenter, and centroid. They all deal with points of concurrency. One of them we get a formula from here, and 2 of them we get a relationship. In-center, your equidistance to the 3 sides. Circumcenter, your equidistance to the vertices. And lastly, centroid, you get this relationship 1/3, 2/3. Okay. By the way, centroid, 1/3, 2/3. What's your relationship between 1/3 and 2/3? What's the relationship between a 1/3 and a 2/3? This is kind of the paradox. It's not a true paradox, but it's a paradox.
1/3 plus 2/3.
What's the relationship between 1/3 and 2/3?
It's 1/3. 2/3 is 1/3 times.
Is what?
Double.
It's a 50% relationship, or 100% if you want to think of it that way, right? You double one, but you double and you're not dealing with a third, you're dealing with a double, right? Times 2 or divide by 2. So when you see this, when I have kids not understand this, is because they can't wrap their heads around 1/3, 2/3 means double 1, divide 1 by 2, because they're thinking thirds. It's third of the whole thing. Okay, so I have this one. Oh, sorry. It is doing something. So short piece is 1/3 green. Other piece, blue, is 2/3. Cool. All right. So here's the one example. We'll call it a day here. You see the 2 medians? I don't need all 3. I just need 2 of them to show the point of concurrency. You see how sometimes it's hard to see the 1/3, 2/3? Right? So where is the 1/3, 2/3? That's actually the harder one to pick out, right? This one is the easier one, but that one, sometimes I have kids just pick the wrong 1/3, 2/3. Okay, so I got a short piece and a long piece. Let's just say, for instance, CF, therefore breaks it into, okay, that's not what I want. I want the next slide. Sorry. 1/3, 2/3. That's what I want. All right, 1/3 of CF would be equal to what? Yeah, but 1/3 of CF would be equal to which piece?
Yeah.
He said CX. It's got to be FX, right? 1/3 of the whole piece is the short piece, right? 2/3 would be, or CX, right?
All right.
Got it?
Yeah.
Okay, now let's go on to real numbers. All right. And this was the point I just made. Has nothing to do with thirds here. It has to do with doubling or halving. All right, here's one with numbers. All right, so I'm going to give you this red one here, CF. Let's put some numbers. You said that was 1/3, 2/3, great. Now, how about some real honest to God numbers? CF is 30. What can you tell me?
1/3. FX equals 15. No, that wouldn't be right.
I'm glad you understood that. What do you got?
10.
And then therefore CX would be? Okay, so there's some real numbers, real math, okay? All right, let's look at the other one, AG. But this time I'm gonna give you one of the pieces parts. Okay, so that's the short piece, that's the long piece. What if AX is 32? What can you tell me? Where are you getting that from? And that's what you got to wrap your head around, is that if you get the pieces parts, the relationship is either double or half. If I give you the whole thing, then you really are doing 1/3, 2/3. So yeah, so FX is, no, XG is 16 and the whole thing is?
48.
You got it. Now, could I throw variables in there? Sure, but this is the key to understanding the whole thing. All right. Have we done enough to be thoroughly confused? 4 words: in-center, circumcenter, orthocenter, centroid. Centroid is the only one we get a formula from, 1/3, 2/3, 1/2, multiplied by 2. And then the first 2, in-center, that's made by angle bisectors, distance between the sides are the same, and circumcenter, distance to the vertices are the same. Yes? You got the answer yet? 105?
I have somehow figured out a way to split a triangle into 3 parts. Not a triangle, but angle.
Oh.
I know, I thought of this too,
Oh.
75. 135 equals what?
135
45.
equals 40.
Okay, so there's a relationship. What number are we trying to get to?
105.
105. Keep thinking.
I've done too much thinking.
90 added to that, 225. Trying to get to 105.
60.
Agree. I'm not saying you can't. If I gave you 180 and we subtract 75, we get 105. But we got to get to 105 from basically what we can do, cut things in half. Right? And we can make 90 degrees and we can make 180 degrees really easy. So the three numbers or four numbers you have to deal with is 180, 135, all right, 134, 135, 90, and 45. Can we make any other numbers with that? Okay, we can get larger, right? Can we make any other numbers? Well, you could subtract these two, subtract these two.
Yeah, but then you just get the same answers.
Agree. So I'm saying it's four numbers, right?
Yeah.
Somehow we got to get to 105 from those numbers. We got to do something because we can make all of those. And we can make larger ones too.
I 15 and 90.
Yeah, but how are we getting to 15?
Yeah, but how are you getting to 15?
Because I said so.
Remember, we don't have a protractor.
I don't have time for this. I have a crusade to go on.
I figured out a way to cut an angle in half. And, well, to cut an angle in thirds.
105, 105.
I don't remember how to do it, but it has something to do with the 90 degree.
Well, I mean, the issue is that 90 minus 135 is 45.
Yeah. 180 minus 90 is 90. And 180 minus 45 is 135.
Doesn't seem possible, does it? Right? I mean, you could start with 105 maybe and try to do something with that.
105 plus 20 equals.
Well, we can't use 20.
I know. We can't use 105 either. We don't have that.
We don't, but if we could get starting with 105 and get to one of these numbers, then we can recreate that process. Right.
Minus 45.
Okay, so minus 45 is going to give me what? 60.
60.
Didn't help.
Minus 90. You get 15. Doesn't help.
It would help if we had a 60 or 30.
Minus 135.
Minus 135 or 105 minus 135 gives us a 20. That's why he was probably saying, I'm sorry, gives us a 30. That's why you were probably saying 30. Seems impossible.
And then 75.
And then the 75.
I feel like it has something to do with parallel.
Well, if we could make another 105, certainly we could create another one, but I guess we're going to turn this into an overnight project then. I thought for sure you'd have it solved by now. Ben, do you have any ideas for 105?
Yes.
Yes.
Well, what are your ideas? Silence.
Well, if you like, you could I'm thinking. Wait, so if line FC is, or maybe it's a bisector, who knows? Oh, wait, they're medians. Okay. Well, if that's a median, that means it's in the middle. Then that.
Ben, we're doing a different problem.
Oh, well, I can't see what's on the, you're not showing me anything except the old problem.
Just 105 degrees. How do we make 105 degrees without a protractor?
Oh, really? That wasn't the homework, 105 degrees.
Yes, it was.
That's why we're talking
You just have to do it. You have to make the thing several times until you get it.
What thing several times?
You know what? I'm going to draw on the screen real quick.
more than 4 numbers? Because then you could have 45. And then
You
have
could.
Technically, have an
You
issue
could.
with numbers.
I mean, we could have, what we make 135.
Always have
So what's half of 135? 67 and a half, right? What's 67 and a half? What was the other one? 22 and a
Yeah,
half?
that's what I did. I did.
Does that get us there? No.
Those two added together are 90 though, I know that.
Well, I know, but we already make a 90, right?
So like, what is this? You want? I did.
I do. Give that one a thought, see if you can come up with it by tomorrow.
And then I did that.
All right, Ben, we're gonna.
You guys want to go on? So I tried to figure out how to do that with a 90-degree angle and a 90-degree
How did you
angle.
make 3?
Well, first I had this line and I had a perpendicular line.
Okay.
And then I bisected it and I had
Okay.
135. I bisected the 135. I got 22.5 here.
Right.
I got 67 and a half here. Half of 67 and a half.
Is 38 and a half, 38 and a quarter.
What did I do here? Wait. Oh no, I bisect. What?
I don't know either.
Wait, what? And then I got 22.5 again. What? I thought I got. Okay.
105. It's hard. Well, it's not easy. I'll put it that way.
Lines of symmetry does a hexagon have?
If it's a regular hexagon, then it has 6.
I'm gonna leave, Mr. C.
Yeah, I already said we're done.
All right, goodbye. Have a nice day.
You as well. I would like to. We're pretty quiet in here after about 5 minutes. They are